Um, Today's topics are going to be black holes, trapped surfaces, and the Penrose incompleteness theorem. So let's just start off. We want to talk about black holes. Recall from last lecture that a space-time is a time-orientable Lorentzian form manifold. So time-orientable means that there is a consistent way to distinguish future from past. We roughly define the black hole region of a spacetime to be a region that has the property that light rays emanating from the black hole region can never reach its complement, while from every point of the complement, one should be able to escape to infinity by following a light ray. And when I say light ray, I mean those are the same thing as null geodesics, because light travels along null geodesics. So in some ways, this is a pretty straightforward definition. It's just the part of the space-time that can't make it out to infinity. The tricky part is that, well, it's not so easy to define infinity here. Defining infinity appropriately in a good level of generality in this context is tricky. So we'll avoid it in this talk. It turns out that it won't matter for a lot of what we talk about later, because the rigorous parts of these lectures actually don't necessarily touch directly on black holes, as we'll see. But they're motivated by black holes. So we just need an intuitive understanding of what it means. The boundary of the black hole region is called the event horizon. So this is the idea that, I'm sure you've heard in popular contexts. The event horizon is something, once you cross the event horizon, you can never come back out. Because once you cross the event horizon, you're in the black hole. You can never leave the black hole again. So we ended last lecture with a discussion of the Schwarzschild spacetime, and the properties that we described for the Schwarzschild spacetime. Basically, we said that if the mass is positive, then there's a black hole region where r is less than or equal to 2m. And now that we have this language, the event horizon is where r equals 2m. So just to bring back up that picture that we had from last time, right, the part that is colored black, that's the black hole region, and everything that's in there, right, it can never come out. While from every point outside the event horizon, it is possible to follow a light ray out to infinity. So in this case of Schwarzschild, and in many other explicit cases, even without necessarily rigorously defining infinity, it's kind of obvious what I mean by infinity, right? So in this case of Schwarzschild, we know what it means to sort of go out to infinity. That's where r goes to infinity. Okay, so it's an important problem to understand which points lie inside the black hole. But this is hard because the black hole region is defined in terms of global properties of the space-time. So it requires complete knowledge of the long-term future behavior of the space-time. So since this makes the study of black holes a little bit inaccessible, this is partly what led Roger Penrose to define trapped surfaces. So we want to talk about trapped surfaces, but before we get into that, I'd like to indulge in a lengthy digression on mean curvature, which is something that probably, again, more people with a Riemannian geometry background are familiar with. So let's let sigma t be a family of surfaces in a Riemannian 3 manifold, with sigma 0 being sigma. So that's the initial surface, or for this, or we can think of sigma t as a variation of sigma. So explicitly, one way of thinking about how do you describe a family? Well, it's the image of sigma under a family of diffeomorphisms. Yes, as I said, this sigma t, we call it a variation of sigma. And for this variation of sigma, we get a first variation vector field just by differentiating the path phi sub t of p. So if phi sub t is that diffeomorphism that determines sigma t, then the first variation vector field is just given by differentiating the path of a particular point as it's dragged along by this diffeomorphism. And so one perspective on this is that you have this surface sigma, right? And sigma t is determined by like every point in sigma's moving, right? So the first variation vector field is just the vector that says what direction each point is moving. So if sigma is two-sided, we can choose a unit normal vector field nu along sigma. This is actually the definition of two-sided. Two-sided means there exists such a vector field, a unit normal vector field. We're just going to pick one. And using this normal vector field, you can define a particular special variation, and it's called the variation by parallel surfaces. The variation by parallel surfaces is defined by choosing phi sub t of p to just be the exponential map of t nu at each point. So basically, what's happening is every point on sigma is moving in a direction normal to sigma at unit speed. And so it's called parallel surfaces because basically for small t, sigma t is a distance t away from the original sigma. Okay, but the path is simple. So you take every point's just moving in a geodesic in a direction normal to the surface. But they're all moving at unit speed. Okay, so the first variation vector field in this case is just exactly the unit normal nu. So in this context, this is actually a decent way to define what the mean curvature is. So the mean curvature, one way to think about it is it's the unique function on sigma such that the derivative of the area form gives h times the area form. In other words, it's basically the expansion factor for the area form. It's how quickly the area form is changing at each point. Okay, so positive mean curvature means that that sigma is growing, right? It's getting bigger. Negative mean curvature means it's getting smaller. Okay, so as I said, d sigma t is the induced area form on sigma t. I mean, technically also pulled back to sigma so that we can actually compare everything, but this is probably a pretty well-known fact. But maybe the usual definition of mean curvature is that it's the trace of the second fundamental form. Right? If you define mean curvature this way, then basically, well, you can prove that this trace of the second fundamental form has this property. Note that the sign of h depends on the choice of nu, right? So there's two possible unit normal vector fields, and if you reverse that, the choice of nu, well, then that reverses the sign of h. Okay, so mean curvature of this family of parallel surfaces, there's a relation to Ricci curvature. So if ht is the mean curvature of the parallel surface, then a fundamental equation of Riemannian geometry states that the mean curvature along that path satisfies a certain equation. Namely, dh dt is equal to minus a half h squared minus this sort of a circle squared minus Ricci nu nu, or nu t nu t. Those are the That's the normal to sigma t. Okay, here, this AT circle, that's the trace-free part of the second fundamental form. So I say this is a fundamental equation of Riemannian geometry. A more common situation that you might see this equation for would be for like geodesic spheres around a point. So the mean curvature of geodesic spheres around a point also have this property, because those are also they're also parallel surfaces to each other. Okay, but here the idea is, instead of starting at a point, right? Instead of starting with the exponential map just around a point, we're looking at the normal exponential map for a surface. So in that sense, it's very similar. Okay. And another way of thinking about it is this is basically true for any level sets of a well-defined distance function. But so in this case, it's the distance from the surface sigma, and as opposed to distance to a point. Okay, so this is a pretty fundamental equation. Something that's worth noting is that, okay, sigma t, right, for large t is not going to be smooth anymore, but for the equation to hold, it only needs to be locally smooth, right, near the point we're interested in. So the equation is valid along this geodesic until we reach a conjugate point. And when I say a conjugate point, I mean a conjugate point with respect to the surface sigma. So the traditional definition of conjugate point, right, you have a geodesic that connects 2 points, and the question is, does there exist a Jacobi field that vanishes at both the starting point and the end point? But here we're talking about conjugate points from a surface to another point. So here the Jacobi field, it's not one that vanishes at the endpoint. It would vanish at the second endpoint, but at the first point, right, it just needs to be tangent to sigma, right? That would also be so when we say conjugate point, we mean conjugate point with respect to this surface, right? Because that's supposed to mean that basically, two geodesics from the surface are essentially focusing in on a particular point. That's the bad situation. It's a conjugate point. That's the situation that would cause sigma t to lose smoothness. Okay. So as long as you don't hit one of these conjugate points, sigma t is at least locally smooth along this geodesic, and therefore this equation works. Okay, so it's perhaps related to the Bonnet-Myers theorem, so the Bonnet-Myers theorem, classical theorem in Riemannian geometry. It says that if you have a complete Riemannian manifold with Ricci curvature bounded below by a positive constant, then it has to be compact. Well, it's one version of Bonnet-Myers. It's stated in a way that it'll be similar to the theorem that we're about to talk about. I want to discuss a similar theorem for manifolds with boundary. It's similar in spirit, and it's also the proof is closely related as well. So this is a Bonnet-Myers-like theorem. It's in a paper by Martin Lee, 2014. I don't know if it ever showed up anywhere earlier, but definitely it's there. And it says that if M is a complete Riemannian manifold with compact, strictly mean convex boundary, and I'll say a little bit about what that means in a bit, and if M has non-negative Ricci curvature, then it must be compact. Okay, so we've replaced the positive lower bound on Ricci. We've just replaced it by non-negative Ricci. Okay, but we needed to have this compact, strictly mean convex boundary. I should say a non-trivial one, right? Can't be empty otherwise. Okay, so here's the proof. I'm giving the equation I wrote down. The proof I'm giving is in 3 dimensions, but actually there's nothing 3-dimensional about this proof. It works in all dimensions. So for every point Q in M, we know there exists a geodesic minimizing the distance from the boundary to Q. Okay, so this is just a consequence of completeness, and this is also why the boundary has to be non-empty. Okay, so as long as the boundary is non-empty, there's a geodesic minimizing the distance from the boundary of M to Q. Well, every geodesic, right, looks like exp of something. So this is exp of T nu for some P in the boundary. But also because it minimizes the distance, it also has to be free of conjugate points with respect to boundary M. Okay. Oh, and also it has to be normal to the boundary as well. That's why I know it has to be exp of T nu, where nu is normal, right? Because if you had a geodesic that was, coming out at a not orthogonally, right, at an angle, it's pretty obvious that it's not going to be minimizing distance, right? Because you could the normal intersection is how you minimize distance to a surface. Okay. So when we take this minimizing geodesic, okay, it has to be normal to the surface, and it has to be free of conjugate points in the interior. Okay. Again, well known. You go past a conjugate point, then it's not minimizing anymore. So okay, so again, let's let sigma t be the parallel surfaces. Again, technically, I really just mean locally defined near this geodesic. So along that geodesic, the non-negative Ricci assumption gives us dh dt less than or equal to minus a half h squared. Okay, so remember the equation on the previous slide, right? There was a term that was obviously negative, or non-positive, so you can ignore that one, and there was a Ricci term, and the non-negative Ricci lets us ignore that term as well. So we have dh dt is less than or equal to minus a half h t squared. Okay, so here's where we're going to use this boundary assumption. The boundary assumption tells us there's a uniform constant c such that h0, right, the mean curvature of the original sigma, is less than minus c is less than 0. So now I'll tell you what the definition of strictly mean convex, if you didn't already know it. It just means that the mean curvature is strictly positive with respect to, say, the outward pointing normal, right? But here, this nu that we're looking at is obviously the inward pointing normal, right? Because Q is inside of M, so the geodesic from P to Q has to go inside of M. So nu is pointing inward, which means that with respect to nu, h is strictly negative. Okay. So h0 is strictly negative is what the strictly mean convex part says. And then the compactness will tell you that, well, actually, then there has to be a specific bound minus c, such that h0 is less than minus c is less than 0. Okay, so here's I think the interesting part, which is that now we have sort of an ODE inequality, and we have an inequality on the initial condition. If you analyze that ODE, you see that ht must blow up before t reaches 2 over c. Okay, right? That's pretty straightforward if you just look at the ODE, right? Like, so if you replace the less than or equal to the equality, right, you can pretty easily see just by solving that it has to blow up. And so since it's less than or equal to, use a comparison principle just to see that, oh, well, then h also has to blow up. Blow up meaning it goes to negative infinity. Okay, so, well, but it can't blow up until we reach a conjugate point, right? So remember, the conjugate point is basically where the before the conjugate point, sigma t is smooth. So what that means is that the distance from the boundary of M to Q is at most 2 over C. And then by compactness of the boundary of M, it follows that M itself is bounded and hence compact. It's a bounded subset of a it's bounded and it's a complete Riemannian manifold, so it's compact. All right, so that's the full proof. Okay, there's a reason why I went through this proof, which is that we're going to go through a lot of similar steps in a slightly more complicated circumstance. So this will give you some grounding for what's coming next. Okay, so now I want to talk about something called the null expansion, which is sometimes called the null mean curvature. Okay, so it's very similar to mean curvature. So before I was talking about mean curvature of two surfaces in a three-dimensional Riemannian manifold. Now I want to talk about a two surface in a four-dimensional space-time. Okay, space-like meaning that it's right, the bowl G induces a Riemannian metric, or another way of saying it, the tangent space is made of sigma is made up of space-like vectors. Okay, so before, in the three manifold, there's only a one-dimensional space of normals, but now because it's a two surface in a four manifold, there's actually a two-dimensional space of normals. Okay, but this is where the Lorentzian geometry is crucial, because although there's a two-dimensional space of normals, there are only two future null normal directions. So just to write this explicitly, right? Suppose our orthonormal basis is E0, E1, E2, E3, where E0 is the time-like one, the future time-like one, and E1, E2, E3 are the space-like ones. And let's suppose that the sigma, right, that its tangent space is spanned by E2, E3. Okay, then it's clear that the normals are spanned by E0 and E1, right? The two-dimensional space of normals are E0 and E1. But in that space spanned by E0 and E1, there are exactly two null normal directions, right? The nulls, right, they don't form a subspace. They're just directions. So the two future null normal directions are E0 plus E1 and E0 minus E1. So just have this sort of picture in mind in general. So now suppose that L is a future null normal vector field defined along sigma. So this is our analog of nu on the previous slide. So nu was just a unit normal, but now I want a future null normal. One big difference here is that we cannot normalize the length of L because it's null, right? So there's no such thing as a unit null normal. So we just have to talk about a null normal. So unfortunately, that means there's a lot more choice for what L could be. But modulo this scaling, there are two possible choices for L at every point. And therefore, for the entire surface sigma, right, there's two choices of future null normal up to scaling, pointwise rescaling. So from here, we're going to proceed in an analogous manner to the variation of parallel surfaces, right? This won't be a family of parallel surfaces, but we can define a variation sigma t by choosing phi sub t of p to be the exponential map applied to TL. Okay, so in other words, every point in sigma, right, is moving in a geodesic in the L direction, a null geodesic, a null normal geodesic. So every point P is traveling along a null normal geodesic, and we're seeing what family of surfaces sigma t is swept out by that process. So here the first variation is L. Okay, so one way of thinking about it, again, it's a null normal geodesic. So this xpt of L. So you can think of it as like shooting a light ray out of sigma and following it for parameter time t. Right? Remember, t has no interpretation as actual time, just a parameter here. Okay, so in this way, one way of thinking about what sigma t is you can think of it as a shell of light emanating from sigma, right? Because at every point in sigma, you're shooting a beam of light out in a normal direction. Okay, for want of a better word, I'll just call this the shell of light family, sigma t. Here we can define the null expansion of sigma in the same way that we define mean curvature. It's the unique function theta on sigma with the property that ddt of the area form is equal to theta times the area form. Okay, so again, it's telling you whether this sigma t, like the sign of it at least, is telling you on whether this sigma t is, you know, locally increasing in area or decreasing in area as you follow this shell of light. One thing that makes this a little messy though is that theta depends on choice of L, but remember, there's all these rescalings. Positive rescalings of L result in positive rescalings of theta. So the lack of normalization means that theta by itself is not directly a geometric property of sigma, but its sign is, right? Whether it's positive or negative is. Okay, so analogous to the equation for the evolution of h along parallel surfaces, we can also get an equation for the evolution of theta along the shell of light family. And the equation is almost the same. So again, you have d theta dt equals minus 1/2 theta squared minus a term which comes from something called the null second fundamental form. It's not terribly important what it is for the purposes of this talk, but just like h is the trace of the second fundamental form, theta can be thought of as like a trace of this null second fundamental form, which again is something I'm not going to define. But then there's also again a Ricci term. Now it's the Ricci of this ambient Lorentzian metric, Ricci of L. Okay, so along sigma t, right? LT is just this same null normal direction coming from the geodesic. Okay, so I highlighted in red because this is a very important, famous equation. It's called the Ricci-Chaudhuri equation in the physics literature, at least. And once again, the equation is valid until the geodesic reaches a conjugate point. Because, again, conjugate point with respect to sigma. Because, again, locally, that's when the smoothness of sigma t breaks down, right? Sigma t is, you know, sort of smooth, at least along this geodesic, until we hit a conjugate point. Nice thing is that reasoning, right, has nothing to do with distance or lengths. Okay, so now we're ready to talk about trapped surfaces. This was um, the crucial insight by Roger Penrose to come up with this. So, for standard sphere sigma in Minkowski space, the null expansion with respect to the inward future null normal is negative, while the null expansion with respect to the outward future null normal is positive. That makes sense. If you have a sphere, right? Imagine shooting light outward. Obviously, that sphere is definitely getting bigger as you shoot light outward. And you take that sphere, and if you shoot light inward, it's definitely getting smaller. So that's totally consistent there, at least in Minkowski space. So a trapped surface is one whose null expansions with respect to both future null normals are always negative. Okay? So this is something that should not feel intuitive, at least if you're the intuition coming from Minkowski space. If you have a surface, right, and you start shooting light out of it, right? I mean, well, if it has some complicated shape, you could imagine, there's some places where it's decreasing, but overall, there should be a direction somewhere where it's increasing. The area is increasing if it, that's possible to more or less prove. But we're looking in an arbitrary space-time. You can have trapped surfaces. So here's a picture, perhaps, of a distinction between, a non-trapped surface and a trapped surface. So the one on the left here, sigma 1, this is what I was talking about. This is a picture that you could have, say, in Minkowski space. In Minkowski space, it's the green arrows are the null geodesics. You follow them along, you're getting something bigger. The second picture is a picture of what a trapped surface might how you imagine a trapped surface might look. So here, the sigma 2 is the green geodesics. Those are the normals, and those could even be thought of as like pointing outwards, kind of, right? Because there's two normals. The inward normal is pointing even more inward, although it hasn't been drawn in the picture. But the outward normal could be those green lines, and yet still, even though it's going outward, the areas are getting smaller. That's a trapped surface. Again, it doesn't look right because I'm drawing it in trivial space, but in a general space-time we have more complicated geometry. So intuitively, the behavior of a trapped surface feels a bit like saying that even though the light rays are directed outwards, like we're shooting them in an outward direction, they're still moving inward in the sense that the areas are getting smaller. So this vaguely captures this idea of light not being able to escape that is inherent in the definition of a black hole or an event horizon. Okay, an event horizon, the light can't escape. Well, this isn't saying the same thing, but it has a vague feel that is a little bit similar. So these trapped surfaces offer us a more accessible approach to thinking about black holes. So this is why I said that we're not actually going to deal directly with black holes rigorously. We're going to deal with trapped surfaces. Okay, so let's go back to the example of Schwarzschild. Where we can see things a little more explicitly. Again, back to the same Eddington-Finkelstein coordinates expression. You can show directly. So if you think about sigma sub VR, so sigma sub VR is the sphere with coordinates v and r, right? So remember, it's a spherically symmetric space. So for every choice of v and r, there's a sphere there. So one can directly show that when r is less than 2m, sigma VR is a trapped surface, while for r greater than or equal to 2m, it's not trapped. So this is the same picture, except now we can look a little bit more on, sorry, maybe it's actually a little small, but you see the sigma sub VR with r less than 2m, that's that yellow that's been drawn there. So the yellow circle at the bottom of that yellow cone, basically that's a trapped surface, and you see that all the light rays coming out of it, even the ones that are pointing outward, right? They don't look like it in the picture, but they are. They're pointing outward. They're still being forced towards r equals 0. So that's why it's called trapped. It's sort of trapped inside there. Okay. Whereas the sigma sub v sub comma 2m, that's exactly sitting on the event horizon. So for along the event horizon, the outward normal will actually just travel directly along the event horizon. So if you just point, if you shoot a light ray out in the outside direction while you're at the event horizon, it's just going to keep traveling along the event horizon. So at least in this simple example, the interior of the black hole region exactly corresponds to the region where trapped surfaces are found. I guess, I'm only looking at the spherically symmetric surfaces, but so it's a little bit simplistic. But that's what's going on here, is that the black hole region is exactly the same as where you have trapped surfaces. The exterior, there are no trapped surfaces. So that's not true in general, that the black hole region is exactly corresponding to where trapped surfaces are found. But in general, we do like to think of trapped surfaces as lying within the black hole region. And in fact, with the right hypotheses, one can actually prove that that's true. But it's also just good for physical intuition. So because of that, instead of thinking about black holes, we can think about trapped surfaces, mainly just because we can do a lot more with trapped surfaces in terms of proving things. It's defined by a nice, local geometry. Okay, so now we can talk about Penrose's famous incompleteness theorem, which was, of course, cited in his recent Nobel Prize. And the Penrose incompleteness theorem, it's a bit much, but we're gonna go try to outline the proof at least. So here's what it says. It says if you have a space-time that contains a non-compact Cauchy hypersurface. So this is kind of the main reason why I put in the definition of Cauchy hypersurface in the first lecture, because it shows up here. So again, the Cauchy hypersurface, it's equivalent to having a Cauchy hypersurface is equivalent to being globally hyperbolic, and both should be thought of as there's sort of reasonable causality assumptions that basically that things behave in a reasonable way. Satisfies the null energy condition, which I will talk about when we get to it. But you should think of it as just a very reasonable physical condition on the nature of the stress energy tensor, on the nature of matter. And third, this is where the important part comes in that we just talked about. It contains a closed trapped surface. So if those three conditions are satisfied, then the space-time must be null geodesically incomplete. So, when this first came out, it may have been thought of as like a singularity theorem. But technically, the right way to refer to it is an incompleteness theorem, that that you're missing something. So why is this theorem so famous? The historical significance is that it demonstrated that trapped surfaces, which are very flexible, they indicate singular behavior. Again, not necessarily singular, but actually just incomplete, but without any symmetry assumptions. So the Schwarzschild solution is very old, though it took a lot of time to be properly understood. But once it was sort of better understood, people did realize that it had these weird properties that we discussed, that namely that there's a black hole in it, and that at the center of the black hole there's a singularity. Okay, and this was considered undesirable for various reasons, and in fact so undesirable that many people didn't actually believe it was true physics. So there was a there it was believed by some that perhaps the only reason why Schwarzschild has this horrible singularity at the center is because it has too much symmetry. So what this Penrose's theorem just completely dismantles that, because it says this has nothing to do with symmetry. It just has to do with having a trapped surface. If you have a trapped surface, then you're going to run into this incompleteness. Okay, so I'm going to outline the proof. I'm not there. Some of the details are I haven't really given you the tools to understand. So let's just talk about some general stuff that I think is maybe the most interesting from the perspective of at least someone like me who has a background coming from Riemannian geometry. Okay, suppose all the hypotheses hold, but also that the spacetime is null geodesically complete. Okay, meaning that every null geodesic can just it can be extended for all parameter time. Okay, introduce this J plus of sigma denote the causal future of sigma. So these are all the points in the space-time that you can get to by following causal curves, right? Time-like or null curves coming out of sigma. See where you can get to from there, right? Basically all the places in the space-time that can be like affected by sigma. So the main step in this proof is to prove that the boundary of J plus of sigma is compact. So again, the boundary of the causal future is compact. Once we've done that, then we'll explain why this contradicts the non-compactness of the Cauchy hypersurface. Okay, so the second part of this argument is the only place where the non-compactness of the Cauchy hypersurface comes in. Okay, so to prove that the boundary is compact, this is the reason why I mentioned Lee's Bonnet-Myers-like theorem, because the proof is very analogous. Analogous, but a little more complicated. Okay, so having a Cauchy hypersurface means that it's globally hyperbolic, and one property of being globally hyperbolic means that for every point Q in the boundary of J plus, there's a null geodesic from P and sigma to Q that is normal to sigma. So hopefully you can see how this is very similar to what happened in our proof of that Bonnet-Myers-like theorem. Okay, so this is similar to how there was a minimizing geodesic. Okay, so let me just say a little bit about the intuition behind this. Is that we're looking at the boundary of the causal future. So the main important thing to keep in mind is that if you are in the time-like future of sigma, then you're not going to be in the boundary. In other words, if you can get from a point in sigma via a time-like curve to some point Q, then it can't be in the boundary, because if it's time-like, then you can find a small neighborhood around it that where there's also going to be time-like, whereas null is on that borderline, right? Time-like is not is an open condition. Null is at the border. So basically, this boundary of the causal future, it can't be connected by time-like curves. It can only be connected by null curves. And in fact, not just null, but they also have to be null geodesics, because if you have like a null curve that is not geodesic, then you can always perturb it to become time-like. And also that's also the reason why this curve that you get here has to be normal to sigma. For a similar reason, if it wasn't normal to sigma, then you could perturb it so that it was actually time-like somewhere. And once you have a curve that's time-like somewhere on a causal curve, you can perturb it so it's time-like everywhere. So anyway, this property of being in the boundary of the causal future, it allows you to do all those same things that, having that minimizing geodesic did in the previous proof. Right. And similarly, yeah, so now we can write it as the exponential map of TL, where L is one of the two future null normal vector fields. So I'll just call them L plus and L minus. So you can always, there are these two null normal vector fields. It's going to be the exponential map along one of them. And moreover, it's going to be free of conjugate points in its interior. And again, it's for similar reasons. If you go, if you have conjugate point, then you can get a broken null geodesic, and a broken null geodesic again has this property that, well, you can perturb it and get a time-like bit, and that'll mess everything up. So the real property we're using is just that you can't have, right, you can't have anything that's time-like if you're in the boundary. Okay, so these features are all similar to what we had before. So just taking this paragraph as a black box, if you want to, you can just think, oh, so now what that gives us is it gives us this geodesic that's normal and free of conjugate points. So now is where we use the null energy condition. So instead of using a non-negative Ricci condition, we use the null energy condition, which exactly says that the Ricci term in that Raychaudhuri equation has the right sign. Okay. So this gives us the exact same equation for theta, d theta dt less than or equal to minus a half theta squared. And the trapped assumption is what tells us that there's a uniform constant c such that theta is 0 less than minus c is less than 0. For either choice of L. Right? Because it's trapped means that theta was negative for both choices of L, and it's sigma's compact, so we get a uniform bound, theta being less than minus c being less than 0, right? And it works for either normal. All right, and once we do that, then the same reasoning as before, the theta t has to blow up before t reaches 2 over c. Okay. Now let's use that null geodesic completeness. The null geodesic completeness tells us that the exponential map, well, it at least exists for all parameter time. For all, right? It doesn't. So now what we can do is we can say, okay, now the boundary of the causal future, what we just showed, is it lives inside the union of all these geodesics, right? All these geodesics that, again, either point out in the L plus or L minus directions, but only up to, they all live in the part that goes up to parameter time 2 over c. Okay. So thus, it's a closed subset of a compact set, so it's compact, right? The boundary is always closed. The set on the right is manifestly compact by its description. So it's compact. So again, this is very, hopefully, to see at least it's very similar to the proof we gave for Lee's theorem. All right. Well, so why is that a contradiction? So here's a picture. I wrote boundary out just to emphasize I'm only looking at. remember there's actually two null normals, L plus and L minus. So I'm just drawing a picture where I'm only looking at kind of the boundary that comes from looking at the outside, not the inside one, just for simplicity of the drawing. So on the left, we have, again, what we think of as like a typical situation, like Minkowski, or something simple. Ignore the omega, I guess. Sigma could be the boundary of some omega, perhaps, but generally what you expect is if you just keep going outward, it just goes out, and you just get this, huge non-compact boundary. The situation we're talking about is, well, how could the boundary be compact? And you'd have to have a picture like on the right, which kind of doesn't really make sense, because that means that the whole future of sigma is kind of like staying inside of that little cap that I have there. But anyway, so now we're going to use a non-compact Cauchy hypersurface to see how we get the contradiction. The definition of a space-time means that there's a time orientation. The existence of a time orientation is the same thing as the existence of a time-like vector field. Right? So there's nothing special about it, just that there is a time-like vector field, a global time-like vector field. I should have said. Non-vanishing global time-like vector field. So the definition of Cauchy hypersurface, remember, it says that all the causal curves, inextendable causal curves, intersect M exactly once. So in particular, if you look at the integral curve of this time-like vector field, well, of course, that's a causal curve, and it's inextendable because you can just follow the integral curve as long as the time-like vector exists. That it intersects M exactly once. So that defines a projection from the entire space-time onto M. But in particular, it defines a map from the boundary of the causal future to M. And here's, again, where we use the fact that no point in that boundary can lie in the time-like future of another. That makes the map an injective continuous map. Right? You couldn't have two different points that are both along the same integral curve of that vector field. So you get an injective continuous map from a compact three-manifold to a non-compact three-manifold, and that's impossible for topological reasons, and that's the end of the proof. Actually, I wrote continuous, but not because it's not, the map isn't better than continuous, is because so technically, so here's the annoying technical bit, which is that this boundary of the causal feature, it doesn't have to be smooth. It's actually only a Lipschitz three-manifold, but you can still prove that you can't have an injective map from a Lipschitz three-manifold to a non-compact three-manifold. It's not as easy because you can't just like use smooth tools, but it's still true. Anyway, so that's it for today, or for this lecture. I hope you continue to join me for the next few. We'll be talking more about apparent horizons and the positive mass theorem.